Hello, everyone. Today we are going to talk about loops. And loops are used to repeat some operations, a bunch of commands, a specific number of times or until some condition is valid. Okay? So when we want to repeat some job and we don't want to keep copying and pasting that line or lines of code so many times, we use a loop, okay, to do that automatically for us. So let's say here I want to do some task that is repetitive, like what? So I want to, for example, create something like a multiplication table or something like that, right? So, for example, for I of 1 to 10, I want to multiply them by 1 to 10 and show the result, correct? So 1 times 1, 1 times 2, 1 times 3 to 1 times 10, and then similarly 2 times 1, 2 times 2, and so on and so forth, correct? The multiplication table, if I want to create something like that, well, I cannot say first display for me 1 times 1, and then display what? 1 times 2, and then display 1 times 3, and so on and so forth, correct? I cannot do that. And then in the next row, I say now display 2 times 1, and then display 2 times 2, and 2 times 3, and so on and so forth. It's not going to work, right? It is going to take lots of lines and lots of copy and paste. Plus, when you do a display and do the next display separated by semicolon or comma, it goes to the next line. So this is not really a very good idea to keep writing, typing, copying, and pasting lines over line to do some basic task. So maybe you want to keep repeating that. So what basically I want to do is something like this. F print F, right? And I want to say what? I times j equals, and then I times j. Now here, since I and j are used for complex numbers, I use I and jj. And here is a simple what? Text. So it is not going to do anything. Here, this I and jj are actual numbers, which can change any one of them from 1 to 10. And here is an actual what? Product. And then I want to include that in this text. So here I say percent u, because they are integers. And then here, in the place of that percent u, I want to do what? I times j. Now, what's the problem here? The problem is this I and this jj will not be replaced by 1 and 2. So maybe I want to do something like this. Percent d times percent d equals percent u, where the first number should be replaced by I, the second number should be replaced by jj, and the last number should be replaced by what? By I times jj. And then give it some space for the next thing. And here, if I simply assign some numbers to I and jj, say I is 1, or let's say 5, and jj equals 8, right? If I run this, so here I make it multiplication table. Okay, then That's the result. 5 times 8 is equal to 40. It added one space, did not go to what? To the new line, correct? By the way, let me dock this back so we can see them at the same time. Now, next time, I can change the value of this 5 and 8 to maybe 5 and 9 and do the same thing. What happens if I do that? You see? Now you get this. If you want, you can add some more space or some comma or something, or add a tab with \t. So it just provides some gap between them. See? If you want, you can even add a comma as well to see where the separation is happening, right? So it's not too bad right now, huh? Good. Now, maybe I can insert just some space too. It's not too bad. Now, if I want to just repeat it for number 5 and change this other number from 1 to 10, I have to repeat this 3 lines, or at least the second and third line a bunch of times, right? So let's say I don't change I because it's constant and 5. So now I have to repeat this line of code a bunch of times, don't I? So it has to be 7, 6, all the way to 1, and on this side it goes all the way to 10. Correct? So I need to repeat this, reassigning J and doing this task of printing 10 times just for I of 5. And then I have to change I of 5 to what? 4, 3, 2, 1, and on the other hand, 6, 7, 8, 9, 10. So you're going to have hundreds of lines of code for a simple what? A multiplication table. So instead of me just copying and pasting these lines of code, now I want this task to be done automatically. How? I allow a loop to basically keep changing I and J and simply running this single line of code, which is fprintf. How? There are 2 major types of loops or operations in MATLAB that are repeating. One of them is for loop, the other one is while loop. For loop is used when you know ahead of time how many times you want to repeat something. While loop is when you don't know, you have to keep doing it until some condition is valid or some condition is violated. In this case, since I know I goes from 1 to 10 and J goes from 1 to 10, I use the for structure. How does for work? For is like this, for, and then you provide the initial value, you provide an increment, and then you go to what? To some final value. Okay? And set that equal to, set a loop counter equal to that. So you say for I equals 1 with increment of 2 to 10, or in this case with increment of 1 to 10, keep doing a bunch of commands, right? So each time this loop counter, which keeps track of how many times your operations have been executed so far, will be assigned to one value by this column operator. First, it will be assigned to the initial value. Then the initial value is added an increment to it and assigned to it. Then 2 increments added to it, assigned 3 increments until you reach the final value. And it's assigned to this loop counter. So in this case, I say what? I say for I starting at 1, going all the way to 10 with an increment of 1. Since 1 is the default increment, I don't need to say something like this. Okay, we know that from previous lectures. So for I 1 to 10, right? For each I, then what? Keep changing J. So here within, for each value of I have to repeat something again. What is that? Keep changing J. So here I can have 2 nested loops and say now, while keeping I constant at 1, keep now what? Changing J. J goes from 1 with increment of 1 all the way to what? To 10. And then what? do this fprintf command, where you show I times j is equal to I asterisk j, and keep adding this comma until what? 1i is done. Now, when 1i is done, I want you to go to the next line. So when I is 10, I want this to go to the next line. Okay, how do you do that? So let's take a look. So what am I doing here? Here I have two nested for loops, correct? Two for loops, one within the other. First, what it does, it assigns I to 1. And then for I of 1, whatever is underneath it will be executed. What is it that will be executed? This other set of commands. Okay, so these lines in this case, 3 to 5 will be repeated. This section of the code will be repeated how many times? 10 times. Each time for one of the I values, I values. Okay, so whenever I is 1, all of this will be done. So all of the numbers 1 times 1, 1 times 2, 1 times 3, all the way to 1 times 10 are shown. There is a comma between them. Now, when the first row is done, I want to go to a new row. So when I'm done with all of this for 1i, now I add one more line. And that is what? Printf, or I can simply say display of white space, which means go to the new line. Now, not only this for loop will be executed for each I, this display is also executed for each I. So the whole thing highlighted will run 10 times. And this one makes sure that when I'm done with one row, I go to the new line and then execute the new operation for the new I and do it. So look now, here we go. You see that? Right? And you have to go up, of course. But here, 1 times 1, 1 times 2, 1 times 3, then 2 times 1, 3 times 1, 4 times 1, and you clearly can see what? Your multiplication table, right? So instead of me copying and pasting so many lines of code, hundreds of lines of code, I did the whole thing with a few lines of code thanks to this for loop. And by the way, as I said, you don't need this increment of 1 because you know it's the default of MATLAB. So that's it, creating a multiplication table like that using 2 for loops. You see how powerful the loops are. They make your code be much more understandable and a lot shorter. Now again, for loop is very good when you know ahead of time how many times you are going to repeat something. Sometimes you don't know. Like, for example, let's play another game. Let's do another code. So in the class when I go and teach, most of the times I don't go with some problems that I worked out ahead of time and know exactly what I should do. I go completely allow the students to decide what kind of problem to code. So I tell them, hey, what kind of problem in real life you want to code in MATLAB? I let them decide the type of the problem. Yeah, I want to do this. I want to do that. How can I code it in MATLAB? And then once they tell me the problem, together we code it. Okay, so I prefer that over just doing something ahead of time and then going. This way, I'm showing them that it does not matter what kind of problem they throw at you, as long as you have the logic, you know how to logically write and solve the problem on a piece of paper, writing it in MATLAB code or any other code, C, Python, it does not matter, you should be able to do it. So let's say here we do a an operation where you have to repeat something, but you don't know ahead of time how many times you're going to do it. Like, for example, what? Let's say you want to guess a number, a random number. I guess a random number, and you keep telling me something until you are at that number, and then once you exactly guess it, you won. I want to know how many times it takes you to guess my number. So this is what I do. I say display this program creates a random integer between 0 and 10, between 1 and 10, and it asks you to guess it, and it keeps asking you to guess it until your guess is right. And it returns the number of times you had to guess until succeeding or success. Okay, so what it does, it generates a random number n, which is rand I of, okay, I max, so 10, and then 1 and 1. So it means it is somewhere between 1 to 10, and I only need one number. Okay? And then keep asking until the guess is right. So how do you do that? You say guess is input of enter your guess. Okay? And you also use a counter. You started at 0 or 1 and do this. While n or g is not equal to n do. So while the guess is different from the actual generated number do, what? Keep asking again. Display your guess was not right. Guess again. Try again. Enter your new guess. Okay, and each time they enter a new guess, add 1 to this counter. This counter is this number that you return, the number of times that you guessed. So the first time you do it, it's set to 1, but each time you do it again, this number counter is going to be updated. You add 1 to it and reassign it back to the variable. This is what you do in C++. You say counter plus plus, correct? You add 1 to it. So here you're updating, adding 1 to it, and then end. So keep asking for the new guess, keep updating the counter, and finally say fprintf. It took you %u times to guess the number, the random number. and it is going to be counter. Okay, it took you 10 times, 5 times. Now, I don't know how many times the user is going to guess until he or she gets it. Since I don't know, I cannot say for I equal 1 to 6, 1 to 4, 1 to 10, or what. I keep doing it until this condition is valid. As long as this condition is valid, this block of code will run. As long as this condition is true, which means your guess is not right. So let's do it now. So I call it while demo. Look. So it explains something, then it says enter your guess. So already it has generated a number n. Okay. And it's interesting that you don't even see n here, because the loop execution is not done. So you don't see the value of n. There is n, but you don't see it. So let's say my guess is 3. Nah, do it again. 7. Do it again. 2. Do it again. 8. Do it again. 1. Yeah, it was 1. Good job. It took you 5 times to do it, to guess it. You see? So it took me 5 times. Now, let me make it one level nicer and then we go. So whenever it's done, I also want to go to the new line. Okay, so here I show the thing. Let's try it again. 4, 1, 9, 8, 4. 4 should not be. 5, 6, 7. Come on. 3, 2, 10. It took me 11 times. That's amazing, right? There are only 10 numbers. It took me 11 times to guess it because I messed up and I entered one number twice. 4. So that's a Guinness World Record, by the way. But yes, you clearly see I'm running a block of code as many times as this condition is not violated. Okay, so that's the difference between while and for. Now, one of the things about loops is infinite loops. Sometimes you provide a condition, and especially for while loop, so you provide some condition that this condition is never violated. And so this loop keeps going forever. For example, now you typically don't do something like this, but you say while true. Seriously? Yes. While true, keep doing it. Look. Enter your guess. 2, 3, 5, 6, 7, 1, 4, 8, 9, 10. You see? I tried all of the numbers, and one of them should be the guess, but guess what? It does not care what my guess is. It's not comparing it to the generated number. It just keeps asking, because I'm saying while true. Of course, this true is always true. It's not going to go false all of a sudden by itself, because this is not a variable that I change. It's not a condition that I evaluate. So this is called an infinite loop. It goes forever. And it never stops. So regardless of what you enter, it keeps bugging you for some new code, some new entry, and you do it, and again it asks, and the code never stops executing. That's a good time to use what? Control-C to stop the execution of a code. Boom. Now the code is terminated. Okay, or let's say you have a surveillance camera, and the surveillance camera wants to keep what? Keep watching and monitoring the outside environment until as much as possible. So then you say, while this true, take video from outside and do it. So sometimes you really want an infinite loop until you manually go and stop the execution by Control C or something, or click on a keyboard key or anything like that, turn some button, physical button on or off. So sometimes you might really want an infinite loop. Sometimes you will you do not want it, but you have no idea ahead of time that this loop will never end, so you're trapped in an infinite loop, okay? Because sometimes it's not as simple as this. So you might say, for example, let me show you an example of that. Of course, it's not going to be infinite, but it's going to take forever to happen. So you start with some initial number of 1, okay? And then you start with some sum of 0. And then you say, while this sum is less than 2, keep doing this. Split n in half, so make it 1/2 of what it was, and then add it to the current sum value. So first, let me add this sum here. And similarly here. So as long as the summation has not reached equal to 2, keep dividing n by 2 and adding it to the sum until you get equal to 2. And this is some of the numbers between some of the terms in a geometric progression, correct? So if you know from that, this is like this: 1 plus 1/2 plus 1/4 plus 1/8. And if you keep going forever, then yes, the answer is going to be 2. But it needs you to go forever until the summation is 2. Okay, so this might take a long time before you get to 2. Theoretically infinite, mathematically until the summation, the difference between summation and 2 is less than that epsilon number, so that MATLAB cannot distinguish between 2 and that number. Okay, so I deleted that last line, and now look, when I run it, actually it did not take forever because MATLAB is doing these divisions and this summation very fast, okay? But if this code here was a little bit longer, it would take some more time to do it, okay? And by the way, one of the things I can do in the code is sometimes I can add some pause to make the execution of the code slower. You can look at the video I made for animation, and you can see that I can add the pause command. And then in seconds, maybe each time I'm dividing in half, I also pause for half a second and then go to the next iteration of the loop, okay? And so here, I'm making the code go a little bit longer, so now it takes some more time, as you can see, okay? It is gonna take some good time because I'm adding lots of pause here. And you see now I have to wait until this long execution of the code runs. And if I find out that I messed up somewhere or I want to get rid of this pause or make it shorter, I can simply do what? A Control C and stop the execution of the code, okay? So that's why I mentioned the infinite loop or long loops and how to stop them, and sometimes you might need them depending on the application. So that's about for loop and while loop basics. Now, there are a couple of more important things that you need to know about them, and that is break and continue commands. So what's specific about that? Let's talk about it. So sometimes you want more control over what you're doing. So let's say here, I still want to create that multiplication table, but I want to skip one row of it. Which row I want to skip? Let's say if this II equals 4, I want to skip it. So it goes to the rows for 1, 2, 3, then jumps to 5. Okay, so I want to eliminate this row. I want to skip over that value. So what can I do? One way to do it is to say, run this for I 1 to 3, and then from 5 to 10. So I have to write 2 separate nested for loops. Or I can do this. I check for this II. If this II equals 4, I skip that. So each time before I run this bunch of commands, I do something. I say if II equals 4, then what? Then skip that II value. How do I skip this whole operation, all of these commands for one specific value? I say continue. Continue means what? Means make your II, which is the loop counter here, from 4 to what? The next number, which is 5. So if it's 4, don't do anything, just continue to the next II. Else, if II is not equal to 4, then do your job. Go for all JJ values, do the fprintfs, go to the new row, and what? Continue to the next II. Except for 4, 4, you don't do anything like this, you just jump over that to next value. So look now. When I run this, you see, the row for 4 is eliminated. Even if you want, you can add a blank line so you can visualize it better. Say if it's equal to what? 4, just create a blank line for me and continue. Now you clearly see it a lot better. Look. You see? I did something different for 4, and I did not do any of these operations. Just directly jump to 5. Sometimes I might do a break. Say, if II equals 4, what? Break. Correct? Break now means what? It's not going to pass II of 4 to 5. It is going to stop all of the execution within the loop. So II will never go to 5 anymore. It stops right at 4 and nothing would happen afterwards. Look. You see? The whole code stopped at 4 and I never went to 5 because I'm breaking the big loop. So break means really stop the execution. Now, if there is a code after this for loop, it will still run, okay? Let's say z equals 99. Look, when I do break, it's just the for loop or while loop that breaks, not the rest of the code. So it's different from return. When you create a return, it will stop the execution of the code after that, regardless of whether there is a loop or not or anything. What break only breaks a loop, not the rest of the code. So break and continue are used within the loop. Return is used outside the loop at any point. Now you might say, what if I use a return here? Can I use a return within the loop? What happens? Well, let's run it. So look, what happened? Did the same thing as break, right? Yes, you see? So return can also break the loop. Does break return? Does break discontinue the code outside the loop? So you see, return does the job of break if you put it inside the loop. What about break? Well, you see here, it does not even like it. It is giving you an error and said break can only be used inside the loop. You can never use break outside the loop as a separate command. You can do return, not break. Okay, so you see in this aspect, return is more powerful than the break command. The break is and continue only used within the loop. Return can be used anywhere. Okay, so that's the difference between these, and these are some control of logic that you can do. So we learned 3 of them. Now, let me talk about one more important thing that is very important, and that is called pre-allocation. Pre-allocation is one of the techniques you use to make your code run faster. Now, let me tell you something. One of the places that MATLAB is slower compared to C or Python, especially C, is loops. Whenever you have loops and whenever you have huge matrices, like for example, pictures, right? I remember I told you pictures are big matrices. Whenever you have lots of data and repetitive tasks operated on these lots of data, MATLAB is comparably slower, considerably slower when compared to C++. And that's why many people try to do some task with C code and run it through MATLAB, and that's where the MEX files comes into play. But here, there are some methods that you can use in MATLAB to avoid loops first, if possible. If not, at least know some methods that if you have to use loops, you make sure your code does not run with a lot of waste of time and without any reason. One of it is pre-allocation. What does that mean? Let me tell you pre-allocation. So sometimes, let's say, you want to create a matrix. You want to create a matrix from scratch. And each time that you go through this loop, the size of this matrix that you create is changed. So initially you start matrix A as an empty matrix, but each time you basically add a bunch of numbers to this matrix A and change the size of it. So you say A is equal to whatever it was, and then on the right side of A, add a random number with size II and 1. What does it mean? Means when II is 1, just generate one random number, 1 and 1, and what? Add it to A. So initially A is empty, correct? Initially A is empty, but then A will be one single random number. Next time that I is 2, the vector you create is a 2 by 1. So you have to do what? You have to come here, generate 2 numbers, and add it to A. Now, how can you do that? Can you concatenate a 2 by 1 by a 1 by 1? Can you do that? Well, let's find out whether you can do it or not and what happens. So first, let's see if this is going to work or it is going to throw an error at you. First, you see, no, I don't like it. What you are saying to me is definitely not working because I'm concatenating arrays with different dimensions. That's not possible, okay? That's not possible. But you can change it a little bit to make it work. How? So maybe one thing you need to add is 1 0 to the previous row, correct? Yes, so when you come here, add a 0 to that previous row, then add this 2 by 1, correct? This way, you make sure that it is going to work. So first, whatever A is, first add a 0 underneath it, then concatenate it with this. Then when you go with a 3, the set of 3 by 1, and maybe 0.1, now you cannot do this. Now you have to add 2 zeros to those previous numbers and do that. So that's one way to do it. And then keep repeating, adding this lower diagonal matrix of zeros each time, and keep going and making sure the dimensions match, right? So that's one way to do it. The other way is, maybe I redefine this problem a little bit. What I'm trying to tell you is changing the dimension of A within the loop. So first time A is a 1 by 1. The next time A becomes a what? 2 by 2. The next time it becomes a 3 by 3. And not only I create numbers for A, I would also do what? I would also resize A. So not only the entries of A are changing, the size of A is also changing. And this operation slows down your MATLAB code significantly. So let's say here, I want to just show you what happens if you don't fix the size ahead of time. So ultimately, the goal is to make A matrix a 100 by what? Sorry, 10 by 10, right? The goal is to ultimately make a 10 by 10. But here I'm not, and you can see it here. If you move your A over this red zigzag line, it says variable A appears to change size on every loop iteration. Consider what? Pre-allocating for speed. So you clearly see what's going on, right? And that's what I want to explain to you. So here, first I have to make sure this concatenation works, right? And as I said, in each iteration, I have to add one row of zeros to A. So when I is 1, I add 1 0. When I is 2, I add 1 row of 2 zeros. When I is 3, I add 1 row of 3 zeros, correct? And then keep going. So what should I do? The thing I need to do is, before this concatenation happens, first I do another concatenation. And in that concatenation, I add a bunch of zeros at the bottom of A. And you see here, I'm using semicolons. So these zeros are added on the bottom as a new row to the current A. How many of them do I need? I of them. 1 row and I columns. Okay, so now I'm filling enough of zeros in, then. So first it's empty, then it's a 1 by 1. When I goes to 1 by 1, it's all good, correct? So here it becomes a 0 of 1 by 1, and then wait. So first I add the random thing. No, actually I have to create that. But when I is 1, I have to do this guy first. Okay. Or I can do something else. I can do, this is I of 2 to 10. And I can just start this with a random number instead of empty bracket. So first I start A with 1 by 1. When I is 2, first I add a 0 underneath A, make it, instead of 1 by 1, make it a 2 by 1. Now I add a random of 2 by 1 on the side. So let's see. There we go. So now A is a 10 by 10 matrix of random numbers. A, you clearly can see that, and there are some zeros at the end. Now, if you look at the execution time of this, using tick and tock that I showed you in one of the previous lectures, look how much time it takes. It takes about, and I run it a few times, now it's interesting that why it jumps to debugging. Okay. Good. So you see the execution time, right? Now, it's not too bad because the size of the matrix is small. Now, if I make it 100 by 100 and do it. Now you see the execution time is way bigger. So the number is 1 to 2 milliseconds. It's, you see, somewhere between 1 to 2 milliseconds, right? Now, if I make it one more 0, now you are talking about a lot more computation time. Okay, now it's 2.81 seconds because now matrix is going to be 1,000 by 1,000. And 1,000 by 1,000 pixel in images is not something uncommon. So you see now my code is running about 2 point something seconds, right? Now I want to do something similar to this, but this time instead of changing the size of A each time, I'm not going to do that. Initially, I would start A with a bunch of zeros. How many zeros? I know ahead of time it should be 1,000 by 1,000. Okay. And then, right, so I started first. And then I keep what? I keep assigning a new row to it. Let's see. Okay, I have to make sure. Oh, I have to now say A of column II and 1 is equal to rand of II and 1. And that's what you need to do. Okay. Make sure. Unable to perform. The size of the left side is 1 by 1. The size of the right side is 2 by 1. Why is that? Well, II and everything. And rand of II and 1. Oh, I see. Okay. Okay. So now I'm going to each row, I assign 1,000 random numbers to it, and I change the entries in A without changing the dimension of it. And if you compare now the runtime is clearly 3 seconds versus 19 milliseconds, right? And I can run it one more time for you. Now, of course, this for loop has 2 commands in it. This one is 1, so they are not directly comparable. But what I can show you in a different example is if you do pre-allocation here, so the size of A in this second case is not changing. It stays at 1,000 by 1,000 all the time. For this one, it doesn't. Okay? And this makes these 2 code run at significantly different computation time. So now let me change it a little bit. I start this with empty, and then I say for 1 to 1,000, A of 1 to II, and 1 to II is equal to rand of II and II. So here I'm changing a minor of matrix A, not just one row at a time. I'm changing the first minor of it from row 1 to row I and column 1 to column I. Okay, so this also, what I'm doing here is I start A as empty, and then each time that this I is changing, I'm changing the size of matrix A. While here, I already started at 1,000 by 1,000. I started at 1,000 by 1,000, all of them 0. And then when I change it, some minor of it, the dimension of A at least is not going to change here. So now they have similar command inside the for loop. So now the execution times should be really comparable. It's not comparing apples versus oranges. Okay, so look here. Okay, so this is a better example than the previous one. I don't like the previous example, but this one is a little bit more reasonable. Now, not too amazing. Let's see. Yeah, kind of, but not significantly faster. Yeah, a percentage faster. Now, I should probably also look for even better examples to show you the computation time difference between them, but you clearly can see the second one is running faster than the first one. Now here, because of the size of matrices, it might not be super obvious. And if you change it to a separate number, it might even be less obvious. You see here? So okay, now it's not even showing itself much. It's 1 millisecond faster. And I made the matrices smaller. When I make them bigger, now it was in 1 second difference, right? And if I make this end number instead of 1,000, 10,000, 4,000, now I expect the difference to grow. Okay, so for handling large amount of data, pre-allocation definitely helps. Although here is just an order of a second. So let me just make it a little bit bigger. Maybe the difference is a little bit more obvious. And one of the reasons is this rand command that is taking so much time that the pre-allocation is not showing itself. So analysis of that is not as obvious, but you clearly see this pre-allocation, and not changing the size of matrix in each loop iteration will help, okay? So now clearly it is taking a lot more time, as each matrix has 4 times more entries. So it is taking a lot more. but I can easily show you that the pre-allocation would help. Okay, that's one thing I wanted to mention, pre-allocation. The other thing is not changing the loop counter value within the loop. That's a common big mistake that you might do. And I'll show you in a second. I'm just waiting for the code to run. So I show you the difference, and then I tell you what I mean by not changing the loop counter within the loop. That's a big mistake that I see many times my students would do. Okay, what does that mean? That means when I'm doing some calculations, okay, now it's 6 seconds. So you see it's quite better. Now, let me tell you that not changing the value. So here, I'm changing this I from 1 to 20, and each time I'm doing some operations, right? So for example, what is the determinant of a random matrix of I and I? So I generate a 20 by 20, 1 by 1, 2 by 2, I by I random matrix, get the determinant of that and show it to you. Okay, that's not a big problem each time. And since I'm not removing the semicolon, you won't see anything here unless I use a display command or I remove this guy, right? Then you will see the results. So here are these determinants from 1 by 1 to 20 by 20. Good. Now, if I make this mistake that here this for loop is supposed to take I to be 1, incremented 1 at a time until it goes to 20. Sometimes I make this mistake of changing the value of this I within the loop. So say I equals I plus 3. What happens? To make it more clear, I'm going to run it 6 times first, so you see better. So look, I run it, and how many times it is shown? 1, 2, 3, 4, 5, and 6, correct? That's 1, 2, 3, 4, 5, and 6. This determinant code is ran 6 times as expected. Now, if I, at the same time, change the loop counter within the loop, now look what happens. Now what? 1, 2, 3, 4, 5 times instead of 6. It ran 5 times. Why? I expected 6, but it ran 5. And you might say, what does 5 have to do with 6 and 3? What is going on? Well, you go with 6, start with 1, and it runs for 1 time. Then here it jumps to 4. Is 4 less than 6? Yes. So it comes back and then do a determinant of a 4 by 4. Right? No. 4 that you generate here goes back, and since I goes to 4, fine. But here, what happens? I becomes 2, not 4, because this line is an assignment. This line now sets I to go to 2. So it creates a 2 by 2, creates the determinant of it. Now it jumps to 5. Goes back here, I becomes 3. Does the determinant of 3 by 3 comes here. Make it 6. 6 is still within the limits. So now, since it's still within the limits, this line runs again, and I becomes what? 4. Creates the determinant of the 4 by 4. Now here I becomes 7, which is out of this limit, so the code stops. So you see, it does not give you something that you expected. And you cannot simply justify it by these numbers. So make sure you do not change, and you can see that here. It says loop index II is changed inside the for loop. Don't do that. MATLAB will tell you something. Whenever you see these red zigzags underneath anything, try to pay attention to them. They are very useful hints. Okay, finally, as I said, one of the ways to improve the speed of your code is using vectorization and avoiding loops as much as possible. Like what? Well, I'll tell you. Let's say the task that you want to do is this. You want to create a sine function, but a trimmed version of a sine function. What does it mean? It means whenever the sine function is positive, you leave it intact. Whenever it goes negative, you make it 0. Okay, that's what you do in a rectifier when you want to convert AC power to DC power, right? Or electric voltage. So if this is your input, you want your output to be something like this. How can you do that? Well, let me show you. So here you generate vector x, which is a linear space of, let's say, 0 to 6 pi with 100 data points, and y equals sine of x. Well, as I said, if you plot x versus y, you get the regular what? Sine function, of course. Now, I want to create a trimmed version of this. How? I have to look into each value of y. If it's negative, I set it to 0. So what should I do? I can do something like this. Say for I equal 1 to length of y. If y at that entry, that location index, is negative, then set it to what? To 0. End of if, end of for loop. Now plot x versus y. Did you see what I did? Anywhere that y is negative, I go and check them one by one. Anytime this is happening, set it to 0, and now plot the rectified sine function, which you clearly can see here, right? If you want, I can add the axis command so you can see better. And let me also use a line width. So between negative 0.1 or 0 to 6 pi, and then negative 0.1 to 1.1. Okay, so you clearly can see that, right? Now, how much time does this take? If you look at it and use a tick-tock, just for this rectification, forget about the plot. How much time? One millisecond, 0.7 milliseconds, right? You have to be careful not to push the button a million times. So you see what I'm doing here. Do it one time, let it finish. Then run it one more time. Okay, so it's a little bit less than 1 millisecond, 0.6, 0.7, 0.8, 0.6 probably, right? Now, if I make the size of this vector y a little bit longer, so let's say I want to use 10,000 data points. So this this for loop has to go through 10,000 data, 10,000 times. Now it should be longer. Okay. It's quite interesting. Seems like it's even really. Okay. 0.2, 0.1. So I'm using lots of data points. So it's about 0.01 or 10 milliseconds, right? So this operation has to be done, this line 6 to 8, a million times here. Now, another alternative to that is something like this. I'm not going to use a for loop. All I do is this. I say, you know, if I say y less than 0, what's the result of this? Yes. I'm comparing each element in y against 0, and I'm returning the locations in y where this condition is happening. So what I'm creating here is a logical array, correct? Which has a bunch of zeros and ones. Now I say y at those locations where this condition is happening, y values where they are negative, set them equal to what? 0. Done. This line 12 does the job of what? Lines 5 to 9. As simple as that. That's it. Y, whenever y is negative, set it to 0. Now look. Do you see the difference? 34 milliseconds versus 4 milliseconds. So here I'm avoiding the for loop. And what we are doing here is called vectorization and logical arrays to avoid direct for and ifs to make your code run faster. And the order of difference between them is not that huge, but clearly you see here, depending on the randomness, but you clearly see 4, 5, 6 times faster, clearly, sometimes like here, 2.5 times faster, but here, I see 6 times, 6.5 times faster, but clearly, definitely way faster. So this vectorization is extremely a powerful command, okay, which avoids loops and allows them to run something very fast. Now, let me show you an example more real life than just working with crazy numbers. So here, let me do some image processing for you. And I'm going to download an image. So whatever image, let's say moon. Let's get an image from the moon. Maybe this one is good. Download this image. Moon.jpg. And what I will do is I will first read this moon into MATLAB. So I say image equals imRead of moon.jpg. That's it. First read it. Now here, you see it does not like it. Oh, because I did not save it as a JPEG. It saved it as something else. Let's see if I can download it as an actual JPEG image. Save image as JPEG. Moon. Save. Now what? There we go. It's an RGB image with 900 pixels, 947. This is height, this is width, and it's RGB. So first thing I do, I convert it to shades of gray. So I say RGB to gray of that image. Okay, I change it from RGB to simply shades of gray, and I can show the image if you want. I am show image. So this is the image with shades of gray without any RGB. Okay, that's what this image is. Now, let's say I want to do something we call in image processing thresholding, image thresholding, or binarization. I want not binarization, just thresholding here. I don't want to binarize. The parts of the moon that are really darker than the rest, I want to make them completely dark. So you see here, these areas are not completely dark like here, but they are relatively dark. So I want to create some holes, black holes, on these spots that are rather dark. Okay, what's a typical value for them? I can look at the data here, tip, and click somewhere. So it gives me the light intensity added. So if you look at the value here, it is somewhere like 0.18, 0.16, 0.18, 0.19, right, 0.22. So this is what I do. I say anywhere where the value added is less than what? Less than 0.2 or 0.25, set it equal to 0. So instead of me saying for II equal 1 to what? Size of image and 1, which is the height of the image, correct? 900 pixels. And for JJ equal 1 to size of image and 2, which is the width of the image, 947, if image at II and JJ is less than 0.25, then set that image pixel to 0. End, correct? And then show the image. And here I use tick and tock to show you how much time it takes for this operation, this what we call thresholding of the image. 57 milliseconds. And here it's not really showing it well. Why? Because I guess it made some mistakes. So 0.25 times 255, because the values of the pixels are not really between 0 to 1, they are between 0 to 255. So now it should be a lot better. There we go. So now I made these black areas, correct? And I can show you side by side with the image itself. So I can do something. I say figure, then subplot of 2 and 1 and 1. I am show the original image, and then subplot 2 and 1 and 2, and then show the modified image. And the original image is something the same as what I read, but I have not modified. Okay. So now you can see them side by side for the sake of comparison. Right? You clearly see these areas are completely blacked out, while these areas are still gray. Or if you want, I can make those areas white actually. If that's the case, then make them 255, make them white. They are dark areas, maybe they are good for landing. They don't have too much volcano and rocks on them. Maybe they are the spots that you want to land your rocket. So make them white. Identify where on the moon you can land, and these spots are the spots you want to land, like Sea of Tranquility or so on, correct? So this is called thresholding, and you clearly see the time it takes me about 49 milliseconds. Now, another way I can do it is this. I will, instead of this 2 nested for loops and if, this is what I do. So I say image, where the image is less than 0.25 times 255 is equal to 255. Anywhere the value of the image is less than this number, set it to 255. And this is what I do. I create image 2, which is the same as image, and image 2 is created by this vectorization operation in line 15 instead of anywhere from line 6 to line 12. So I replace line 6 to 12 with a single line, line 15. The result of that I call image 2. And maybe here, actually, I call this one image 1. And so I change image 1 and image 2, but not the original image. And I make this a 3 by 1. And I also show you image number 2. And maybe I add a title here, say thresholding using vectorization. Correct. And then I add some titles for the other ones too. So this one is original image. And this one is thresholding using nested for loops and if. Okay, so if I do it, you see the results are the same. But if you look at the runtime, you see here the vectorization is done 3 times faster. And if you do it more, you see the order of running is each time 2, 3, sometimes faster. Okay, so let me run it one more time. You see this time is about 8 times, 7 times faster. Run it one more time, 4 times faster, right? So definitely vectorization speed up the operations. Make sure don't loop the change the loop counter within the loop, and make sure to pre-allocate everything. That is what I'm doing here, pre-allocation for image 1 and image 2. If you want, you can set them equal to zeros of the same size as image. That's okay. As long as the size does not change. Okay, so I guess I have told you enough about writing loops and improving the code speed. So I would stop the lecture here, and in the future lectures, we work on using these loops and the logics that we learn to solve more complicated problems.